Okay, so this this work has been done by Brian Jones, who has been my student for a couple of years. And the motivation for this talk has been that there has been lots of interest lately for using bubble-based therapies. And here's an example of blood-brain barrier opening in a pig brain. So you can see nice opening of the blood-brain barrier, and that can be used for drug delivery. There are also some thrombolysis and histotrypsy examples where bubbles are used to magnify bioeffects, and those treatments are very close to be used in clinic testing. All the animal results are very, very promising, showing that it has lots of potential. But in order to do this in clinic, we need to know what the bubbles are doing and where the bubbles are activated in the brain. And for that purpose, passive acoustic mapping has been proposed to be used. And but for brain applications, the PAM has the problem that the signals have to go through the skull, and the skull distorts the field, so the imaging is not very, very good. So just briefly, PAM technique is very old. It was proposed in Japan about 35 years ago. And it's simply where we have a hydrophone array. We have acoustic sources. In this case, these are bubbles that are activated by the therapeutic ultrasound. The exposures are long, so these are not just short pulses, but the bubbles are vibrating, like in blood-brain barrier case, about 10 milliseconds. So we have long time to collect the signal with the hydrophone, and then we have the signal for each hydrophone, and we just time shift these to form the image in 3D. So it's all dependent on aperture. And if the signals that are not coming from the source, of course, destructive, and we don't have combined signal, but at the location where the source is, we have an interference pattern that allows us to localize the source. So this is fairly simple, but in practice a little more difficult. We have been applying this technique for trying to localize microbubbles through human skull during blood-brain barrier opening, and for that we use our experimental array that has 1,372 cylindrical transducer elements that are transmitting their sound at about 300 kilohertz. And elements are designed so that they have a hole in the middle, so we could put a hydrophone in, and we didn't have quite large amount number of hydrophones, so we put on 128 hydrophones, and those were localized in an optimized sparse pattern. Try to get the signal, see if you can image the locations of the bubble vibrations. So for this work, we are now looking how to do the skull corrections typically in treatment when we use high powers to treat brain tumors for our brain disease. We use CT-based numerical models that predict phase corrections and then use for the transmit sound. Similar models have been used for passive imaging. We have tested those, and they seem to work well through human skull. In a clinical setup, the patient is put in an MRI scanner, and the treatment planning has to be very fast. So we cannot calculate a complete field patterns, and we have to use approximations. And for those cases, we use ray tracing technique and simplified models, and they seem to work reasonably well for those treatments. So now the objective here is that testing can we use these simplified models also for the passive beamforming. And then if there is any cost, how large that cost is for the system. So we again use the same array. In this time we used PCT receivers at the second harmonic frequency. We are transmitting 300 kilohertz and receiving about 600. And Then we used a CT-based model with full wave equation simulations is our standard. And this is the experimental setup. So we have a good human skull that is sitting in deionized water inside the array. And then we have three-dimensional positioning system that has an ultrasound source that is moved inside the skull. And then we go in different locations inside the skull. And we used, this is coronal across the skull, and this is along the length of the skull. So we have different locations. We used 4 ex vivo human skulls and 106 different locations. And our source was not quite optimized to the receiver array, but reasonably close. For the simulations, we used measurements that were done in the laboratory a few years ago for sound speed as a function of density derived from the CT image. And for this frequency, we had to interpolate from the measurement with the 2 other frequencies. And here you can see the attenuation in meters per meter as a function of density. So high variability as a function of frequency. And so we used these numbers in our models to simulate the wave propagation. For the full wave model, it took about 7.8 hours to simulate the 128 received signals or do the corrections. And for the fast analytical model with using array acoustics, it was 127 seconds, so it is much more reasonable for treatment purposes. So here are some examples. This is the time here, and there's a normalized amplitude. This is the signal without any skull, and this is without the skull, and this is with the skull. So we have this adjustment that we have to do to get them to overlap. So the skull caused time difference is 2.4 seconds here, and these are now the no skull measurement, and these are the heterogeneous skull model and homogeneous skull model for the full wave model. And this is the analytical model where we just take the CT-derived skull density information and correlate that to sound speed. And so this is how the sound speed is going to vary inside the skull. And one model we calculate the average number, and the other one we use the distribution along that line in the middle of the transducer element. And here are just some of the examples. So here is no correlation. You can see that the focus is destroyed. This is across the focus, and this is along the focus. So without correction, you cannot really see where the bubbles are. And now if you use the invasive correction wave, meaning that you use actual measurements to obtain the correction values, we see reasonably well. You can see that the array is maybe has too few elements. It's not quite exact. There is like grading lobes, but the location is fairly good. With the heterogeneous correction, we get almost similar results. Homogeneous is less good, and so forth. And the fast model is not as good. When we look at it as a function of location inside the skull, we notice that the closer we come to the skull, the worse the SNR is. And of course, the invasive source gives the best values in the full wave model than the next, and then no corrections gives you the worst values. The analytical corrections are better, but not ideal, and same in all 3 directions. And then when we analyze, this is a percentage of errors over and here's the index of the error numbers. So you can see that here, in most cases, the positional shift errors are less than 1 millimeter. And here is the PP volume. Similarly, typically, most of them are less than 5 cubic millimeters. And these are now the numbers are for the area under the curve, and you can see that the full wave model gives you the best numbers in all cases. and this is peak side lobe ratio similarly, so it's about, in most cases, it's about 25% side lobe ratio, in some cases it could be 50%. And SNR error is here, again showing the same trend. Corrections make a huge difference. The model, and showing also the models are not perfect, so even the full wave model is not perfect. We could do better than that. We tested this in animals, in rats, and in this case we used 5 cycle burst, repeat once a second, and this was 2 minutes sonication, which is a typical length for our blood-brain barrier opening. We used 3 rats and 4 targets per rat, and these are the images you can see. So here is the MR image, so in this location there was no blood-brain barrier opening. With this sonication, and then number 2 there was a blood-brain barrier opening, and here are the corresponding signals from the imaging, and you can see no correction. You kind of can maybe guess that the location is there. With source correction you can well see where the location is, and same way with CT correction. So both work reasonably well in this case. And here are the metrics, no corrections. We gave about 2 millimeter phase shift, location shift, and SNR is about 67% what it could be. Whereas with full where we get 0.8 millimeter, which should be reasonably good enough for first in clinical trials. The analytical solution gives 1 millimeter error, so maybe not too bad. So as a conclusion, it looks like analytical models can give you some improvement for image quality. It's not as good as full wave models, and even the full wave models need some improvement. So thank you very much for your attention.